So it's my pleasure to introduce our final speaker for today. Shuran Song is an assistant professor at Stanford University. And before that, she was a faculty at Columbia University. Shuran received her PhD in computer science at Princeton University. Her research interests lie at the intersection of computer vision and robotics, and her research has been recognized through many awards, including the Best Paper Award at RSS 22 and TRO 20, the System Paper Awards at CoRL 21, RSS 19, and also finalists at RSS, ICRA, CVPR, and VIRUS. She's also a recipient of the NSF Career Award, Sloan Foundation Fellowship, as well as research awards from many companies like Microsoft, Toyota, Google, Amazon, and JP Morgan. Yeah, I'm looking forward to your talk, Shuran.
Thank you so much. And hello, everyone. Good afternoon. Thank you for staying to the last talk today. Yeah, so hopefully today you have heard enough ideas and thoughts about how to mastering the robot manipulation in a world of abundant data and get excited about that scenario. But I think my talk will be first focused on this first order problem of how to get to the world of abundant data, which I think is like a lot of people agree that we are not there yet, right? So first, maybe let's start by just quickly discuss why we don't have abundant data for robots. There are many obvious reasons, but there's also like some more subtle and less obvious reasons. Right? So for example, the obvious reason is that if we want to collect robot data, oftentimes it does requires you to have some robots. So robot has cost. But I think more subtle reason is that thinking about data collection for robots actually has much higher operational cost. Right? So if you want to collect robot data in many different environments, that requires to ship your robot around or like just like move them into different environments. And also another cost that oftentimes people don't talk about is the expert cost. You need someone that's trained to kind of learn how to tally up robots and then also be good at it. So if you look at a lot of like very impressive tally option demos, actually I'm always curious about who tally up that data because sometimes it's actually really hard to tally up. So those are some hidden costs. And then what about internet data, videos or texts? I think the biggest problem for those data is that you don't have sufficient information. So obviously you don't have a lot of detailed robot action data. And also I think a subtle reason is that most of those data does not have those multi-sensory data that you need, like force and tactile, which is very critical for manipulation. At least I believe very critical for manipulation. And then the last part is about the reusability about data, right? Even if the data is so hard to collect, a lot of grad students spend a lot of time to collect their tally of data. Oftentimes the data only can last for one project. And then after that, you need to like switch to a different set of data. So the reason for that, like when we don't reuse data, oftentimes is because data we collected are very task and also robot specific. Meaning that if you change your robot hardware a little bit, you move your camera a little bit, you cannot reuse the data. So as a result, a lot of those data has a very short shelf life that we just keep recollecting new data. So that is also a problem, like why we don't have large robot data today. But if you think about if we aggregate all the data that we already collected for robots, like with all the grad students across the world, it's actually quite a lot. It's just we don't reuse it. So today, my plan is to talk a little bit about our work and then use them as examples of how we can potentially address some of those challenges about data collection for robots, and then potentially like kind of paint a way of how we can get there for a world of abundant data for robots. So first work I'm going to talk about is this work called UMI, which stands for Universal Manipulation Interface, and the short is UMI. So what is UMI? So as you can see, UMI is a handheld gripper or a handheld device that allows you to do data collection. Like anyone can take this gripper to do data collection for in many environments, almost any environment can just take the gripper to that environment and collect data for many different robot manipulation tasks, like including very challenging ones like folding clothes or tossing objects. And then finally transferable to many different robots. So in our paper, we test this policy on 7-degree freedom robots, 6-degree freedom robot, expensive ones or cheap ones. So in order to do that, we have a few like carefully designed hardware and software interface to make sure that the data is transferable and reusable, right? So from the hardware perspective, our goal is really try to make sure that the data collection device is able to capture sufficient information for policy learning but still at the same time, reducing the embodiment gap between the human data collection and the robot execution. So to do that, what we designed is a few important design decisions on this gripper. First is that we use a fisheye lens on our camera to capture very wide field of view image so that we can encode enough visual context for inferring robot actions. And then we also add a little, like 2 small little mirrors on the side. So that is to help the system to kind of get a different perspective to the same view to help them to get a sense of 3D depth information. That's what we call implicit stereo. And then in order to capture sufficient action information for the robot learning, we first add a small code on the finger base so that we can track the continuous gripper width. So that is actually quite important because we don't want to just have binary controls of open and close. We want this, the policy able to precisely control the timing of opening and also the exact width of opening. So that's why we need to have this code on the finger to track that information. And also we use visual SLAM to track the camera pose in order to recover the accurate 6-stop robot actions in terms of action trajectories. And then on the finger side, we use soft fingers to give you a little bit passive compliance so that when you collide with the object or collide with the wall of the table, you don't break your finger. And also, when we read the paper, we say that this kind of deformation give you this implicit force information because you observe the deformation and you know how much force you apply. But in reality, what we found is that this information is quite limited because the type of material we use, actually, if it's too soft, it cannot pick up heavy objects. So, and if it's too hard, you actually cannot see much deformation. So later I'll get back to like how we can enhance this force feedback or force information later. But I think, yeah, so far actually with just this, it's a little bit hard to gauge the force information. Okay, so I think most importantly, I think the thing you need to remember for this design is that we really try very hard to make sure that this interface can be applied for different robots because it only use wristband camera and only look at the gripper. You can easily adapt it for any kind of robot arms you have. So that's why we call it universal diffusion interface. So in the end of the day, all the data that you collected for the task you care about is just a single MP4 file. And you can easily decode all the information necessary in order to train an effective policy, including, for example, detailed robot actions, multi-sensory observations, and also you can like include task instructions through narration. And we really hope that this single MP4 file data format is already so standard, so easy to share. We can use it as a shareable and a reusable data format for robot manipulation, so that eventually we can share across labs. Okay, so if you read the paper and look at the website, you can see that UMI is actually quite capable. Like we showed a lot of complex manipulation tasks like tossing objects, folding cloth, or even doing like dishwashing and like cleaning dishes. And then, yeah, there's a few demos on the website you can see. But today I want to kind of focus on a slightly different aspect, which is the portability of the data collection device. And as a result, allows us to collect data in the wild, right? So because the system is so portable, the whole handheld gripper is very light, very small, you can carry it around into any different environment you care about, like your home, your kitchen, and then collect the data that you care about. So for this particular cap rearrangement task, we actually collect over 4,100 demonstrations across 30 different environments. But in total, we actually only take 12 person hours, which is quite like short. If you have multiple people, that's like actually just one afternoon, you can collect all the data. And then in the end, we trained one policy that covers all this training data. So as a result, the learned policy actually can like generalize to new environments that it has never seen before. And it's actually like, I feel it's pretty impressive. Like for example, we just dragged this robot across Stanford campus, and most of the environment is actually outdoor testing that we never collect data on it. So for example, on this water fountain, we never collect data on a water fountain. We only collect data on actual tables. But the robot is able to work out of the box on those scenarios because of the diverse training data it has seen. So just to quickly recap for this UMI project, what we addressed is kind of like the first bullet point of the challenge, right? So because we don't actually need a robot in the loop to tally up, so the cost of data collection coming from the robot is much lower. And also because it's so portable and then you can easily take this thing, get into different environments. You don't need to worry about the shipping cost. And then because it's just a handheld gripper and very intuitive to use, you can pass it to your friends. And then you actually don't really need to train your robot expert to tally up those data. So that is the first challenge for data collection. How about sufficient information? So I would say that for UMI, actually, it does collect almost sufficient information for learning robot policies because, like I said, we track the grippers, we do the scan, we have the end effector poses. However, I have to say that the data collected by UMI, at least this current form, does not contain rich enough tactile or force information. That is actually very necessary for manipulation. So how can we solve this problem? So in the second part of my talk, I will actually kind of mostly focus on a few extensions of UMI that's really thinking about how to add tactile and force feedback to the system. And then I think just give you a quick motivation. One of the reasons why UMI is much easier to do data collection tally operation is that you actually get very natural force feedback and haptic feedback when you're doing data collection. When you're doing tally operations, a lot of times you need to use your vision to gauge whether you're in contact or whether the action is precise. But when you carry a UMI, the force feedback is very natural. So that's why it's kind of intuitive to use. However, the problem is that while you are getting this information, while you're doing the data collection, the robot, when it executes their policy, they don't have that information, right? So when the robot is executing learning its policy, all it has so far is just a visual feedback. So it doesn't have any force or tactile feedback. So how can we address this problem? So today I'm going to actually talk about two of the projects that's actually trying to address this force and sensing feedback problem from slightly different perspectives. One is thinking about what kind of sensing device we can add. And the other is thinking about how we can reformulate the diffusion policy or the policy formulation in order to better use those force feedback information. So this first project is called ManyWave. So in this project, we actually try to give robots a sense of touch or tactile feedback through audio data, like the data that you captured through microphones. Right? So this may be a little bit counterintuitive at first, like why we want to capture tactile information or force contact information through a microphone. But if you think about it, it's also actually quite surprisingly interesting. So the audio feedback that's captured through a contact microphone actually provides very rich information about contact, right? So for example, it can easily tell you that when your robot is in contact with an object, what kind of object you're in contact with, and it even can tell you very detailed surface material information if you're just sliding through the surface, right? So for example, in our project, we actually test on this very interesting task where the robot actually can tell the different surface of a Velcro tape. So if you use a Velcro tape, you know that they have two different sides and the surface material is different. So in this case, the robot actually able to touch the surface and hear the sound feedback that while it's touching the surface and able to distinguish which side of the Velcro tape is touching and select the right one to do the task. Right, so this kind of very detailed surface material information is actually even very hard to capture if you have very high resolution, like for example, gel size sensor. Because this the difference is so subtle and so detailed, unless you have very, very high resolution tactile sensor, you will have trouble capturing it. But a $5 microphone is able to allow you to capture this information. So I think the best part of using a contact microphone as a approximate tactile sensor is that this sensor, you can easily buy it off the shelf today from Amazon, and it's very cheap, $5, $10, you can get this contact microphone. And then even better is that when you get this microphone, it comes in with a very standard interface that you can directly plug in into the GoPro camera that we are already using for UMI data collection. Right? So you actually don't need to think about all this complicated electrical design in order to hook it up with your data collection system. And also it's automatically synchronized with your video data. So you also don't need to worry about the latency problem. And then I think also very nice is that this contact microphone almost never breaks. So if you ever have experience working with tactile sensor, you'll know that most of the gel side actually worn out if you use it for prolonged period of time. And also oftentimes you need in-house expert to know how to maintain and fix your tactile sensors. But if you use a contact microphone, you don't need to maintain it. As a result, you don't really need to have an in-house expert. It's just plug in and play, very easy to use. So all this property really make contact microphone such a low cost but high return investment. So I would say that if you're thinking about making a robot to do any contact-rich task, you really should add a contact microphone to your robot. So I don't think you'll regret it. It's just a good deal. And then, however, there is indeed a small challenge or quite obvious challenge when you're thinking about using contact microphones in your robot. And I think that is come from like the background noise that you have. In particular, if you're using like UMI type of device to collect data. And so here I'm not playing the sounds, but you can basically imagine that when you're using UMI, like the handheld gripper to collect data, your contact microphone will pick up some background noise or like people talking in the background. And when you're running the robot deployment, like executing the policy, the action, the system will actually pick up a lot of noise from the robot motor. So this is actually really loud, and then it's actually vibrating quite a bit. So there is a domain gap, or like kind of like the distribution gap between the demonstration data and the robot data. So how can we bridge this gap, right? So that is actually a pretty practical problem. So during this project, we actually tried out a lot of different signal processing tools and methods. And in the end, what we found actually works the best is actually a surprisingly simple data augmentation method. The idea is that you have your data, original data collected that is relatively clean or has some noise, doesn't matter. We just add a lot of random audio data into this data set, just directly overlay it, and also some robot noise. And then use this augmented signal to train the policy. So what this policy learned is that I should just ignore those irrelevant noise, but focus on the task relevant part of this signal. So with this data augmentation, we can train this policy, basically train a pretty standard diffusion policy with these two sensor modalities, and we can actually execute, like deploy the policy for many different contact-rich tasks. So I guess just a quick summary of some findings in our paper. I think the first thing is that we do find that if you include contact audio, you can actually improve the robustness and the generalization ability of your policy. So here is just a quick visualization for the attention maps that the policy learned with and without audio. So one interesting thing we found is that when you are training the policy with audio, the policy is more likely to focus on the task relevant area. So for this task, it's trying to wipe the marks on the whiteboard. So if you train with audio, it actually focuses on like the shapes on the whiteboard. But if you don't train your policy with audio, if you only train with the vision, the network actually focuses on the room structures, like for example, the table edges or the room boundaries, and instead of focus on the whiteboard. So the reason is that without audio, the robot really have trouble knowing when it's in contact. So it's actually trying to use the room structure or the edge of the table to gauge the depths. So it's kind of overfitting to the wrong places. But with audio, it's very easy to know that when I'm in contact with the whiteboard, therefore focus on the right part of the problem. And another, I think, quite obvious finding is that we found that the noise augmentation is effective, although it's very simple, in bridging the audio domain gap. So if you're using audio, you're thinking about using audio in your robot, I think you should always consider using this noise augmentation. So this is actually not surprising because in vision training, we actually always add data augmentation, right, to make the policy robust. So I think here is the same story, that we add data augmentation in the audio to make the policy more robust. So many wave is good. That is like, it gives us a little bit tactile information than before. However, it also has a few limitations that I have to mention. So first is that while the contact microphone does provide information about the contact event, like when you're in contact, it does not provide you with very precise the force information. It does not tell you that you're pressing the surface with 1 Newton of force. So that information is not there. So as a result, one common type of failure modes that we see is that for the wiping task, sometimes the robot is able to wipe the shapes off, but sometimes it just use too much force because it doesn't really know how much force I'm applying. I just know that I'm doing the job. So sometimes it actually, like, see, it's always bending the finger because it's squeezing too much. So that's one problem. It doesn't have very precise force information. Another problem is that It's more come from the policy formulation. So we still use diffusion policy that's just predicting the position of the end effectors. So as a result, the system, because it only predicts end effector pose and does not using any compliance, so it's actually not very robust to any unexpected force perturbations. So I think both of those limitations actually lead to the thought that I think we still can benefit from, like, if we can use real, like, precise force feedback, and then also combine it with like proper compliance control, so that it can better leverage the force information. So for example, here is a system that we can, or like what task we can do if we actually use accurate force sensors and also training a proper adaptive compliance policy. So you can see that this policy is able to precisely follow the very complicated 3D curvature of this vase, and it's also able to maintain the constant force in order to wipe out the marks from the vase. And it's also very robust to perturbations. Like the student actually like try to knock down both the robot and the object, and it's still able to work. So to be honest, I actually see a lot of diffusion policy deployed in my lab and also across other labs. I kind of believe that this is one of the most like graceful and robust policy that I have seen, at least in my lab. And it's not trained with tons of data. It's just by leveraging better using force sensor, right? So if you actually really think about how I can get my policy into next level, that it just works better, smoother, and more robust, more elegant, I think maybe thinking about other sensor modality would be another direction instead of just adding more data. So how we do this? So this is the paper that we just submitted to ACRA. This is led by my postdoc Yifan. It's called adaptive compliance policy. So the idea is quite simple. It's that we want to add compliance or like force feedback into diffusion policy. However, the challenge for adding compliance, or the tricky part about adding compliance into your system, is that the compliance profile, or the target or desired compliance profile, is oftentimes task dependent. Like depends on task you do, that you probably has a different target compliance profile. And also it is something that will vary or like change temporally and also spatially, depends on the stage of the task. So it is a highly dynamic property that if you just manually tune that compliance profile, it's very hard to get it right if you're changing from task to task or like different stages of the task. So so actually, because of that, if you look at most of the existing systems that's using compliance, they oftentimes actually just use a constant compliance that is uniform in all directions. So as a result, it's very hard to find the right compliance profile for the given task. Right? So for example, if your policy is too compliant, it's actually will lose the ability to track the target very precisely. So as a result, you may lose context at some point. And then on the other hand, if the is too stiff, you easily break your robot or tool or object because it just does not provide you enough compliance. It doesn't mean that you can just keep tuning it and get the right parameter. It's actually really hard because it's not the one single parameter. Your compliance actually will change before contact, after contact, and also depends on the pose that you're actually doing the task. So getting the right compliance is hard by manual tuning. So what we can do, we can learn it from data. Right? So that's basically the idea for this work, that we're trying to basically summarize the desired compliance profile from human demonstrations. And then we'll train a policy that's able to quickly and dynamically adjust the compliance based on the visual and the force feedback. Right? So the policy is the same as diffusion policy, but the input has additional force, and also it has additional output to describe the desired compliance profile for your low-level controllers to execute. So just high-levelly describing the output, that's the policy basically representing the desired compliance by using a virtual pose target and also a target stiffness value. So those are the things that learned through your human demonstration data. And here you can see that the robot actually, through their execution, when the virtual target is aligned with the position target, it means that the robot will be very stiff and actually track the position very precisely. And then when they're deviate, means that you want the robot to be more compliant. And then the directional difference between the reference target and the virtual target give you the compliance direction. So you can actually adjust the compliance direction in 6DOF as well. However, as you can imagine, this policy actually works really well and is able to like really gracefully handle this very complex context-rich task. But there is one quite big limitations that I don't really like about the system. That is that it really relies on a very expensive and also like hard to use force sensors. So we use the ATI force torque sensor in each of the robot end effector in order to get this force feedback. So as you can imagine, if we want to do data collection, now we need to kind of do data collection with these robots with this very expensive force sensor. That is kind of going against with my UMI design, right? I don't like that. So I think one thing that we are actually working on is try to improve this whole system design by making the force torque sensor smaller and more portable. So this is still ongoing work with my new postdoc, Ho-Jun, also from Stanford, that basically Ho-Jun's whole PhD thesis is about this coin FT. So this is actually a coin-sized force torque sensor that's very small. Like this is the original ATI sensor, and this is a coin FT sensor. And then you can see the plot of the force feedback from these two sensors that, although it's not maybe as precise as the ATI sensor, but it's highly correlated that you can actually get a pretty good force feedback or reading just from this small force torque sensor. So with this small sensor, we actually can add it to our original UMI design and then make the whole data collection device portable again. Right? So this is something that I'm pretty excited about, and we are actively working on it. So that is about the last point, is getting sufficient information, in particular force and tactile feedback. How about the last thing is reusability of the data, right? Can we reuse the data for different robots, different projects? So this indeed is the most common questions I get asked, is how to make the UMI system or UMI policy workable for a different robot. So I think for that question, it really depends on the type of robot you have, right? If you have another industrial robot arm that comes with a very precise and accurate IK, then pretty much the policy is directly transferable. You can deploy the same policy on a different robot by just calling the IK solvers provided by the robot. However, if you have a mobile robot or legged robot that does not come with like a precise IK solver, then what you need is actually a whole body controller that learns, like for example, in this case is a legged robot. So what we need to train the whole body controller to do is to learn how to move your body and legs so that you can achieve certain end effector trajectory that's predicted by the manipulation policy. Right? So here you can see all these errors is basically the manipulation trajectory that's predicted by diffusion policy from data collected by UMI. And then the whole body controller is trained to kind of able to track those end effector trajectories. So the good thing about learning this whole body controller is that nowadays you actually can train this whole body controller purely in simulation without recollecting any real world data or simulating any real world tasks, right? Which is actually the most expensive part. Like for training the whole body controller, you just need to load the robot. You don't need to load any robots or any objects or any tasks. So that's actually make it very easy to learn. So when you have the whole body controller, you just need to combine it with the manipulation policy that we trained with the real world UMI data. You can get very expressive real world manipulation skills on those very complex legged robots. So for example, you can do this kind of like a very fancy task of like tossing tennis balls. And then to collect the data for this robot, you just need to actually use the UMI gripper, like a handheld gripper, to collect tossing trajectories. And then the simulation data will learn how to control the robot body. And then I think what's more exciting is that once you have this system, you actually can directly plug in the original UMI policy that we trained for the cup rearrangement task for this legged robot, and it was immediately zero-shot work onto a new different robot embodiment. So that means that we can completely reuse the data that we collected in the earlier project. And for this UMI on-like projects, we actually indeed directly using the policy that we trained on UMI. We didn't do any fine-tuning, didn't do any like data collection. And then if any of the things I talked about today interest you, you can check out our project webpage. For all the things I talked about, like apart from the ongoing projects, we always try to open source our code and also give you very detailed tutorials about how to build the UMI gripper. So we really hope that there will be like more UMI grippers around the world so that people can collect data. And then I think it's actually indeed true that a lot of people are already using UMI, printing UMI across the globe and building their own systems to collect data. Here it's just like 2 example works that I feel particularly impressive that people actually build UMI like in Tsinghua, and also here is Shanghai AI Lab. They actually also even improve the UMI to have a better tracking results. So that's also one of the pain points for like the UMI. Sometimes the SLAM doesn't work. And then I think there's many other works actually using UMI currently. And then I think like it's very encouraging to see like they're using it. And then also in order to, so just to help people or build up this community that people like share different data, we recently launched this data website. It's called UMI Data, UMI-Data. And the goal is that we really try to build a centralized hub or like a place to share different UMI data that's collected across the globe or from different industry or academic labs. And then if you are also using UMI or some related data collection device, you can actually contact us to list your data here as well. I highly recommend you to do that. You can also like start from our own project. We actually already shared all the UMI data that we collected throughout different projects. And then we really believe that there's no data set that's too small. I think one of the reasons that people back then don't really share their robot data is that they may feel like, oh, my data set is so small. It's only a single task, like 100 data points. But I don't think like that's a problem. Like even you are just having a single task data set with a small number of demonstrations, you should consider listed here because it will eventually add up, right? And then also we, yeah, oh, oops, so, okay. Okay, so the last point is that we really believe that UMI is a constantly involved design. That even if you are using, if you're thinking about adding new sensors or tweaking the hardware and make the device different, then you can still contribute to your data, even if it's not directly transferable to our current UMI design. It can still be used for pre-training or other creative usage, right? So regardless, I think you should consider share your data in this website if you are using UMI, or you just directly use the data that's already listed here. And that's the end of my talk. Thank you.
Thank you very much for the great talk. Are there questions from the audience? Okay, we can start here. Most.
Yep. Thank you very much for the talk. Basically, the tactile sensor you mentioned, the audio has been developed by Giorgio Cananta 10 years ago.
Yeah.
So what is the difference?
Yeah, I think the sensor itself has no difference. It's just a microphone. However, I do feel like in terms of how to use it, there's a slight difference. So I think before, the reason why people don't use microphone as a way to like get tactile sensor is because it's very hard to get explicit contact information, right? So if your policy requires like contact position or contact force as an input, then it's actually very hard to explicitly decode that information and then put that into policy. But if you learn it using behavioral cloning, you actually don't really care about explicit state information. You just need the raw input. So that makes it easier to use the microphone type of data.
Then basically, then what you were presenting, for me, there is no autonomy, it's more automated grasp, right? Because when we are talking about the vision and tactile, and we want to make the robot to be autonomous, to grasp the manipulation, the robot has to understand the visual properties and tactual properties. And the tactual property doesn't come with just with a simple contact, because it's action condition, right? Tapping, patting, scratching, sliding will give you completely different information.
Exactly.
So this is a tactile.
Yeah.
And when you are talking about the microphone, and the reason even the Giorgio stopped working on, because it doesn't give you tactual information. It's not a tactile.
Yeah, I don't think I fully understand your question, but I think, for example, indeed, the feedback really related to the action strategy. Like we show that when you touch the surface, you can actually hear the feedback instead of just directly touching it. You need to like sliding on the surface. So, but instead of asking the robot to infer the strategy, we just demonstrate that strategy. And then the robot can learn directly from human demonstration. We simplify that process. So hopefully that's like answer your question. Maybe we can have more discussions afterwards. Yeah.
Maybe for the sake of time, we can one or two other questions from the audience. Yes, please.
on the top. So
Mhm.
just
You mean the deformation, right? Yeah, so I think when we read the paper, we actually make a point that you actually can estimate the deformation from the finger, or estimating the force from the deformation. But it's actually kind of hard because the material that we use is kind of like stiff. It doesn't deform that much. And when we change it to very soft material, it cannot pick up very heavy object because it bends. So that's a problem. Yeah.
Yeah, then maybe one more question from over there. Yes, please. Yeah.
okay. Yeah, like,
Yeah, I think both are very good questions. Let me go back to the first one. I think I didn't say that contact microphone is sufficient. I think that's why we are still trying to add force sensors. So I think contact microphone only give you, for example, a very high frequency information. It does not give you precise force, also does not give you the low frequency like force information. So I think contact microphone is a very convenient way to get a little bit like tactile, but definitely it's not the best way. So if you have money, like better. If you can design your tactile sensor, then go for it. I think that's still valuable. And then for your second question, I kind of forgot. Yes, about whether the force is the action or the, yeah. So I think in our current system, although it's a quasi-static task, actually it's not just taking force as an input and use it as a feedback. The output is actually very important as well. So it also infer, so the virtual target, you can think about that actually telling the robot that what is your expected force that you need to execute in order to do that task. You can imagine that for wiping tasks, you need a certain force. We also in the paper, we test on different type of tasks like rotating, pivoting an object that requires a different type of force. And also the force needs to change when you're like actually moving the object around. So it's already part of the output and it's already part of your action space for the force. That's true. Yeah. So I think for the tasking task, although back then when we do it, we don't have those feedbacks. I think it will benefit from force and tactile feedback. Yeah. Yeah.
Thanks again to our speaker.